This is Stefan with his talk on iOS kernel heap Armageddon. Let's give it up for Stefan.
Thank you. It's okay? Okay. Let's get started. I have far too many slides, so I hope I'm not too fast. The title of the talk is iOS kernel heap Armageddon because it's showing a lot of stuff about the iOS kernel heap and some new way to exploit the iOS kernel heap. Yeah, I can skip through that. I'm from Germany, I'm from Cologne, and in the past I did a lot of PHP stuff, now I do iOS stuff, and yeah. Okay, in the beginning a little bit, a small disclaimer. So I might mention iOS 6 throughout the talk several times. So whatever I say about iOS 6 is, maybe changing tomorrow because iOS 6 is in beta. And because the beta is only available to registered iOS developers, I would be under NDA if I talk about iOS 6. But I don't have an iOS developer account, so I cannot break the NDA. So everything I talk is basically information that was leaked to me. Okay, so why this talk? When you look at the past research of the iOS kernel heap, you will see that basically it was always similar based on the work from Nemo, who did this for macOS. So in iOS it's a lot similar. So there is a kernel heap zone allocator. It comes with heap metadata. This can be exploited, and this is one possible way. So basically everything that was said before about the iOS kernel heap is exactly summarized like that. So I want to talk about something different. So of course in the beginning I will just wrap up the what's known beforehand about the iOS kernel zone allocator. And but I will talk about other kernel heap managers and wrappers that are existing, about recent changes in these allocators, about the idea to have cross-zone attacks. I will get into this later, what is meant by that. And we know that from user space heap exploitation, nowadays you don't go after the heap metadata, you go after the application data. And so I will talk about some kind of kernel application data that you can override to get code execution. And in the end, I will present a generic heap massage technique for the iOS kernel heap. Well, much similar to what you do with JavaScript in browsers. Okay, let's get into this zone allocator quite fast. So the idea of the zone allocator inside the kernel is that the kernel heap is divided into so-called zones. And each zone starts with a first chunk of memory. And it's usually one page, but it can also be multiple pages. It depends on the definition of the zone. So when you want to see what zones are existing, there's a tool called setprint, which also works on macOS. And when you execute that command, it will show you all the zones. And you can see here that there's a lot of information about each zone. First you have the name of the zone, you have the size of the elements in the zone, the current size of all the memory that is allocated to the zone, the maximum size for this zone, the number of elements, the maximum number of elements, how many of these elements are in use at the moment, the allocation size. This is basically what I meant. You see a lot of 4K. These are all the zones that have one page zone elements. And there's some zones that have they're bigger. So every time the zone has to be increased in size, they will allocate more than one page. But the majority of zones are just 4K zones. So here's the first time I mentioned iOS 6. So basically this setprint tool is based on some Mach APIs that give all this information to user space. And in iOS 6, Apple has closed these APIs by checking if the function PE ICANN has debugger. So this should be only true on Apple debugging hardware that most probably exists and on jailbroken devices. So on a factory, you shouldn't be able to execute that on a factory device. So therefore, it's no longer usable for kernel heap exploits. So in the past, this was used because it gives all this information, like I go back. So it gives you like the elements, the current number of elements, and so on. So it's very nice to know this information if you want to do heap massaging. But Apple has closed that road. So now you have to use different techniques. Okay, so let's continue with the zone allocator. So basically we had like allocated this first page, and now this zone is divided into memory blocks of the same size. For example, you have a zone where each element is, in this case, 512 bytes in size. So each element inside the zone is 512 bytes. And once this is divided logically, then the heap manager ensures that it remembers these blocks, and the first 4 bytes of each free block is a pointer to another free block. So each time a new page is added to the zone, it will add all these new free blocks to a free list. And it does that in the opposite direction. No, it builds the free list, so it first puts in the first element and so on. And of course, therefore, the head of the free list at the end is the last one that was inserted, and therefore the memory is actually used backwards. So the first time you allocate, you get like the last element and the next and so on. So when you allocate memory, it's not like you allocate something and then the next element would be afterwards. It's before, in a completely fresh zone. Yeah, so of course there's this free list, and when memory is allocated, the allocator looks into the head of the free list that is stored in the zone structure, and this points to a free block. And what happens now is it will take the first 4 bytes of this block, and because that is the pointer to the next element, it will take this pointer, make this the new head of the free list, and then it will return the free block. So in case of a buffer overflow from one allocated memory block into a free memory block, you can of course override the pointer to the next element in the free list, and therefore you control the next pointer that's returned when this element that was free, when this is returned by the zone allocator, then you overrode the first 4 bytes, and that means at this point, these first 4 bytes will become the head of the free list. So you basically control where the next allocation, what memory block is returned as the next memory block for the allocation. So, of course, Apple has seen all this, and now in iOS 6 they have changed this a little bit. So you must know in the past there were already some debugging code that would like do Morse checks and overwrite all the memory and use some kind of tagging. But this was always disabled on factory phones. And now in the iOS 6 betas, it seems to be that there's now memory tagging that writes a fixed value after the free list pointer. This doesn't stop the exploitation at all. It only stops the exact vector that was used in all the public iOS heap exploits. So what was done in all these public iOS heap exploits is they would like make the head of the free list some pointer in the middle of the syscall table, and then the next allocation would return actually a pointer inside the syscall table, and when the kernel writes data into this memory block, then the syscall table is overwritten and you can control where the code execution goes. And of course, because now there's this memory tagging and you don't have this tag value somewhere in the syscall table, you cannot return a pointer inside the syscall table anymore. So this just fixes this one path, but still a lot of other ways to exploit this are open. Okay, so this was all this information, well, except for the iOS 6 editions. So this is the information that is basically public until today. Oh, well, actually everything here is public because I gave this talk before. But this is basically, this was the information that was originally maybe done by Nemo and then ported by me to iOS, and this is what the last year everybody was talking about. This is what's used by all these public jailbreaks at the moment. So now let's look at the other mappers and wrappers. So this is not a complete list, but you can see here there's a bunch of functions inside the kernel that get used to allocate memory. On the right side, on the left side, for example, you see some operators, new and new array. This is because there's some C++ inside the kernel. So, but you can see there that this basically uses kernel OS malloc, and this again uses kalloc and so on. And you can see what function inside the kernel calls another function. And in the end, most of this ends in kernel memory allocate or in setalloc, which itself are they're interworked themselves. So this is basically what you need to know. There's like this hierarchy of memory mappers, but most of them are just wrappers, and they call other memory mappers. Let's start with looking at kalloc. Kalloc is basically a wrapper around either setalloc or kmem-alloc, and it adds no additional heap metadata. So it's most probably not interesting to look at it for exploitation purposes because there's no extra heap metadata. The special thing here is whenever you use setalloc, you need to know a zone this memory block is stored in, and because kalloc allows you to allocate arbitrary sizes, the caller has to keep track of the allocated size so that it can, when it frees the element, that the allocator still knows in what zone this memory was put in. So, and the thing is, for small memory requests, the zone allocator is used, and for bigger requests, the kmem-alloc is used. And like I said before, kalloc needs to determine the zone, and basically kalloc creates a bunch of own zones. You can see these zones with setprint again. And this is like an output from iOS 5. So you can see there's a bunch of zones, and nowadays these zones are not necessarily powers of 2. In the past, there were only powers of 2, starting with 16. Now they're starting at 8 bytes and have some completely not power of 2 numbers in there, like 48 or 112, 88, and so on. Well, I guess the reason for that is that there's a lot of memory allocated in these intermediate zones, and by making the zone size smaller, the element size, you don't waste so much memory, and so that's better for like a mobile device. As I said in earlier talks, changing the smallest block to 8 bytes is actually quite useful for some exploits. Okay, so like I said before, there's kalloc and there's carefree for freeing the memory again. And there's some kind of protection in this whole k-free code path because in the end, when it frees memory, it keeps track of the largest allocated memory block. Actually, the memory mapper below that, the kmem memory allocate, is doing that. So they keep track of the largest allocated memory block, and if you try to free something that is larger than this block, this is just a knob, so it will just be ignored. So this will also not crash, it will just be a knob. And I think it increases the counter inside the kernel, but I don't think anybody cares about this counter. Okay, so kalloc didn't bring any kind of heap metadata, so it's just a wrapper and not interesting for exploitation. But there's another memory allocator called _malloc. And this is again a wrapper around kalloc, and it adds extra heap metadata to the allocated memory block. And this is like, it adds a 4-byte header which contains the size of the block. So the caller of malloc doesn't need to keep track of the allocated size because the allocated size is basically inside the block itself. And there's a specialty about this function. Unless kalloc, it doesn't allow you to allocate 0 bytes memory blocks. So if you do a malloc of 0 bytes, it will return a null pointer. And you can see that here inside the code for malloc in iOS 4. And this is just like a slide showing that in iOS 4 there was a possible integer overflow inside this function that was silently fixed in iOS 5. And you can also see that a request of null bytes is answered with a null pointer. Yeah, and as I said before, in iOS 5 they now check for this buffer overflow, this integer overflow that could lead to buffer overflows. And now the difference is basically you can no longer achieve code execution through these kind of attacks. So if you can control the argument to malloc, the size argument, and put something very large inside, you can only cause a kernel panic. Okay, so what happens when you overwrite data that is allocated by malloc? It's you can only overwrite the size field, because it's the only extra metadata, and this allows you 2 different things. If you write a value in there that is smaller, then when it's returned to the memory, you basically leak memory. Because it will be, the large buffer will be returned into a zone that is supposed to have smaller memory elements. So there's a lot of memory that leaked in this case. And in the other case, if you write a bigger value in there, then the memory manager will return it to the wrong zone, which is expecting larger memory blocks than this actually is. So this means the next time this fake element in this bigger zone is returned, and the kernel writes into it, it's actually writing into a zone element that is supposed to be much smaller, and then you can then you have a normal buffer overflow. Okay, so as I mentioned before, there's this kernel OS malloc and new array, and they are very similar, like malloc, especially this kernel OS malloc. It looks a little bit like copy and paste, which means they also copied the integer overflow, and they didn't fix that integer overflow in this position. So if you find a place where you can influence the size argument to kernel OS malloc, you can still trigger this integer overflow and exploit it possibly. I think at the moment there's no such call, but maybe in the future. Well, I guess tomorrow this bug is fixed. Anyway, so but aside from that, it's very similar to malloc, and the operators new array just wrap around it. There's a special case for the new array allocator, because when you try to register an array of 0 bytes, of 0 elements, then it will return a buffer of 1 byte. Okay, so the next thing is this mcache slab allocator, and that is very complicated and doesn't fit into this talk, because otherwise I can talk for hours. And so maybe in the future this is a talk by itself. And so the last one that was interesting here is this kernel memory allocate. But when you look at it, I think this is a quote from the Apple source code. It's called the master entry point for allocating kernel memory. And it allocates a memory in specific memory maps, and it always allocates whole pages and if you request a lot of memory, more than 1 gigabyte, it will fail and just return a null pointer. I believe it returns a null pointer and doesn't crash. Yeah, and it keeps metadata, but it keeps that in a different position than the memory itself. So the metadata is outbound, not inbound. So when you overflow some block that was allocated with kernel memory allocate, you're not accidentally overwriting the metadata. So this seems very uninteresting for now. Okay, so the next thing that I was interested in is, okay, now we know how to exploit attacks against a zone allocator, but what about, for example, I have an overflow in a kalloc 32-byte zone. What about another zone? Maybe there's something interesting like a function table that is stored in a zone that's called blob, and it's also 32 bytes. So now the question is, can I or a different size. So the question is, can I see if these zones are in memory right next to each other? Is a position like, can I massage the heap in a way that one zone is exactly behind the other and so on? So I did some experiments. Yeah, okay, that's what I said. So I want to see what's the position, the relative position of kernel zones to each other. What's the position of pages inside the same kernel zone? So if I have like a full page and I overflow the last block inside a page, what will happen? Will it crash because there's no memory afterwards? Or can I abuse the memory manager in a way so that the next zone that is added to this, the next page that is added to this zone is basically in memory behind it? Yeah, and what is about, can I do a kernel level heap spray? So. Okay, so and what I did is I did an experiment. I patched an iOS kernel to give me directly access to the kalloc function. Kalloc. To the kalloc function, and basically from user space I could just call kalloc and it would return the pointer to user space, so I can see what pointers are returned by kalloc easily. And what you can see in iOS 5 is that everything that is returned is between these values, 80000 and so on, and 8ffffffff. Basically, you can make it even smaller, but let's let it like this. And what I wanted to do is I wanted to visualize where in memory are these allocations. So I just wrote a simple user space tool that would allocate 48 megabytes of kernel memory and then just visualize where in memory these pages are. So in the beginning, you don't see much. After like 100 allocations, I think that you cannot see it so good. There's some, in the lower third, maybe there are some red dots, and all over the place there's some smaller red dots, but yeah, there's basically a line. Okay, but now do more allocations. You can, I don't know if, can you see that? Yeah, because from here it looks like you cannot see it because the color is too bad. Okay, so I would just do more allocations and you can see it gets red more and more and more, but it's basically all over the place. Okay, so, oh no, that was the last one. Okay, so you can see basically the pages that were returned are completely distributed over the area. Of course, in the beginning there's this black box because it's like actually the kernel image and the heap is behind that. What's interesting here is while it's very random, you can see that there are clusters. So in the top there's very, very much red. So it seems that although it seems random, actually there's a high probability that the memory is up there. So what I did next is I thought, okay, now let's try that again. Try this actually 25 times, which is very hard. if you have to do 25 times in going to DFU mode and do limerain exploit and then like boot this patched kernel and so on. So that took a while. But in the end I had all these results and now tried to like overlay the results. So what I did now is I just added all the pixels to each other and divide them by the 25 reboots. So you can see here there's still, in average, there's still a large cluster in the beginning which is very red, so the memory is quite often returned up there. So the next thing I did was, okay, now let's check if actually the memory pages that are returned are common. So is there one page or is there a set of pages that is returned in all 25 reboots? And yeah, in 25 reboots I found one page that was always allocated. Problem was then I tried this 26th time and then it was not allocated. So basically that means you cannot have one fixed address that you maybe hard code, and you cannot ensure that with a lot of allocated memory that you actually have allocated this piece of memory. So heap spraying is basically not really feasible. However, I forgot to say that on the first slide. The problem here is this only, or the good thing here is this only applies to the zones that are single page zone. So this only applies to these zones where one page is added to the zone when the memory runs out. Memory that's allocated in zones where there are multiple pages is handled differently, and it usually are pointers above C00000. Yeah? Yeah.
Yes, I wanted, do you find code in Z-alloc or K-alloc that does this non-determinism on purpose?
Actually, so far I only did these experiments. I didn't search for this randomness. So far I didn't find this code by accident or so, but I didn't explicitly search for this. Okay, so what I wanted to say here, there's other zones where there are multiple pages allocated at once, and these zones basically are allocated above C00000, and those are actually adjacent. So if you choose memory from these zones, you can do a heap spray and actually have predictable addresses. Okay, this is only true for iOS 5, so with iOS 6 there's this kernel ISLR. I'm not a developer, so I didn't test it yet. It might be now different, so that you cannot ever rely on a heap spraying in this case. Okay, so the result from this is you cannot just overflow outside of a zone page, because there's a high probability that the memory after this page is actually not allocated. So if you overflow at the end of a page, then it will just crash. So all your attacks must be always in the same page. And then the question was, when you look at cross-memory allocator attacks, like I have one memory block that's allocated with kalloc and the other one is like allocated with kernel malloc or so. So the question is, if I overflow this one memory block from one allocator, can I overflow into the other one? And the answer is yes, that it's possible, because it's possible for all those allocators that basically in the end all call the set-alloc allocator. Like, you can overflow memory from new, so you can overwrite objects from a kalloc area and so on. And that's what brought me to the next idea. So now the question is, I don't want to attack heap metadata. I want to attack heap application data. And so in this case I do a C++ object case study. Of course there could be other kinds of things inside the kernel, like maybe function tables that you can overwrite, but for now I'm just interested in C++ objects. because inside the iOS kernel there's this IO-kit interface, and there's this libkern which supports C++ for kernel drivers. And yeah, I think outside of IO-kit it's absolutely not used. So everything that's C++ inside the kernel is somehow related to IO-kit or to the implementation of the C++ thing. And the runtime, the C++ runtime it comes with, so it's not a full runtime, it's just like a small runtime. And the runtime it comes with comes with a set of base objects that are below the actual IO-kit objects. So these base objects are shown here. So you have something called OS object, and nearly all of the objects are basically derived from that. And then you have like collections like sets, ordered sets, dictionaries, and OS arrays. And you have a bunch of other things like data, strings, numbers, booleans, yeah, and something called the iterator, which is used to iterate over like collections. So now, when you look at these OS objects in memory, they will look like this. This looks very much like C++ objects in browsers, or like in user space. So you have like, in the beginning, you have like the vtable pointer. And in the case of the OS object, you only have one property, which is the retain counter, which is some kind of reference counter. And the vtable pointer is pointing into the, I think, const segment of the kernel. And this is basically the list of the list of methods of this object. Well, the virtual functions. Okay, so the other thing that's in this object is this retain count, which is actually interesting because it's not a simple reference counter. It's a 32-bit field that is split into two halves, and the lower 16 bits are real reference counter, and the upper 16 bits are collection reference counter. So the kernel keeps track how often this object is inside the collection. And the funny thing here is that the reference counting stops at 65,534, and if you have like an object that has more references, or when it tries to create more references, we'll just like ignore those and not increase them, but it will also not decrease them anymore. The moment this number is hit, it's just frozen. So this object cannot be freed anymore. So this is very simple. If you have a way to create that many references, you can leak memory and just easily crash the kernel by just creating a lot of objects. Because in the end, the kernel doesn't have memory anymore.
Excuse me? So what's the use of upper 16 bits then? Is it for optimization or?
Like I said, the other 16 bits are the reference counter. So he asked what the other reference counter is used for, the upper ones. So this is, like I said, just collects how often this is added to collections, and I believe it's only used. Yeah, I think it's only used inside the deallocation to see if suddenly the original reference counter drops under this collection reference counter, and in this case the kernel panic is thrown. I think this is the only place where this is actually used inside the kernel. So it's basically waste. Okay, now the interesting thing, what happens if you have like this object in memory and you override it? So, because there are only like two things in there, so you can only override these two things. And when you look at browser exploits, you see they always try to override the vtable pointer. And you can do that the same in the iOS kernel. You just override the vtable pointer, and the next time the kernel tries to do anything with this object, it will basically use the function table you supplied by overwriting the pointer. Okay, in this case it might be tricky to actually have, you have to put this function table somewhere in kernel memory and then like, let it point to it. But yeah, of course you can do that with information leaks and all this kind of stuff. And the other thing that you can override is like the retain count, and this might allow you to introduce use after free vulnerabilities into the code, and then you can exploit them like normally, like let the object be freed, get a new memory in the same place, and then you again control the vtable pointer and so on. So let's look at a different object. So you have the OS string object, and this has some more properties, so you can do more. For example, when you override the flex field, you can control if, in the end, on the destruction of this object, if the kernel tries to free the string or not. So again, you can do this attacks like returning this into the wrong KLOG zone and so on. No, wait a second. So now the next element that you can override is the length, and this is basically similar to when you override the length field inside a malloc block. So you can like put it in the wrong KLOG zone, and therefore it will use either it will be useful for heap information leaks or for like freeing memory into the wrong zone, so that you can maybe trigger a buffer overflow afterwards. Or sometimes you maybe just want to leak memory for heap massage. Yeah. And the last thing you can override is the string pointer itself. The string pointer is basically a value that is allocated with kalloc, and it just contains the string. So of course, if you can override this pointer and later read the string, for example, through the registry and the IO registry, then you can leak kernel heap information, or again, you can free arbitrary pointers the moment this string object is destroyed. The next thing that's interesting is the OS array memory layout. And this is a little bit more complicated. So you have like far more properties in this case, and one of these properties is the array pointer. And the array pointer is also allocated with kalloc, and it allocates capacity times size of void pointer. So basically it allocates a table of pointers that all point to either to null, if there's nothing in there, or to an other object. So that means if you can overwrite the array pointer or the array itself, you can basically make the kernel use OS objects that are actually fake objects and they are supplied by you. And any action the kernel performs on these objects, again, will result in code execution. And if you overwrite all the other fields in there, the count, the capacity, and so on, then again you can do this kind of things like info leaks, because you can like read uninitialized memory, or you can again do these confusing attacks to so that memory is returned into the wrong kalloc zone and so on. Yeah, there's also two properties called update stamp and f options, and I think they are not really usable. So if you overwrite them, you don't can leverage that for code execution. Okay, so this is just like a short introduction of how these C++ objects look inside the memory. And now you should know that by overwriting them, you can do like execute code inside the kernel, like you can also do in browsers. Okay, and now that we know that we have these objects, the question is, can we like do a kernel heap massage in a way that's like a little bit more generic and that allows us to override these kind of kernel objects? So when we look at heap controlling techniques, there are basically two. There's this heap spraying, which basically is just filling up the kernel heap with arbitrary data. And then there's this heap feng shui or heap massage, heap setup, heap layout control. There's so many different groups of people that prefer to call it differently. In the end, it's all the same technique. The idea is we have like an unknown start state and we want to bring the kernel heap into a known state. and doing this by carefully crafting allocations and deallocations. And when you look at the public exploits that already exploit the heap for iOS, I think there are only two, mine and the one from POT2G, they always use very vulnerability-specific ways to allocate and deallocate. So it's not generic at all. And my idea was I wanted to have a more generic solution that can be used for all kinds of overflows. Or not all, but many of them. Okay, let's look again. Heap spraying means we need something to allocate repeatedly. We need to be able to allocate attacker-controlled data. We need to be able to allocate large quantities of data in a row. And usually we want to fill the memory with some specific pattern. Heap feng shui, on the other hand, is a little bit more complicated. We want to allocate repeatedly to actually close all the memory holes. We want to be able to allocate arbitrary sized memory blocks. We want to be able to poke holes into these allocations so that we can control the memory layout. And of course, we want to fill the memory with interesting data, application data, so that we, when actually trigger the vulnerability and overflow something, we want to overflow something or to heap corrupt something that is basically interesting to corrupt. So, and when I looked at the iOS kernel, I found a very useful function, which is called OS unserialized XML. So what is this function? This function is a kernel function, so user space cannot call it directly, but basically, no, not all, but a lot of IOKit API functions will allow the user to submit like objects in plist format and XML plist format, and then the kernel will basically unserialize this XML to create objects. For example, when you open an IOKit driver, you can give it a bunch of properties it should start with, and then it will call this function to like deserialize the properties. But there are like many other things, like when you want to match something, you also supply this, and in many API functions, you basically are able to pass user control data to, or you're supposed to pass user control data to this OS unserialized XML. And this is very powerful because it can create, the data objects among the base objects. So you can create numbers, you can create booleans, strings, data, the dictionaries, arrays, sets, and you can also create references. And it's in plist format, so you can see it's XML, and you see in this case it's a dictionary with 3 keys inside, and the first key is there, and there's a string value. The second key has a Boolean true value, and the last key is again a string value. Oh yeah, before the talk I removed a bunch of slides because that would be just too complicated and it's not really useful in this case. So this is a leftover that might be useful or not in this case. So the thing is just, the idea here is it's a memory-sized cheat sheet. So if you create an OS array in memory, the OS array itself is 36 bytes in size, but because it's allocated through kalloc, it's put into the kalloc 40 zone. And additionally, when you create this OS array object, you will allocate more memory, which is capacity times 4. Because inside an array, you only have pointers to the objects of the elements. Because an array is just numerical index from 0 to the end, and so you don't need to keep track of keys. Which is different for OS dictionaries. There you have the capacity times 8, because you always have 2 pointers. The first pointer is the key, the second pointer is the value. Yeah, and so on. So this is just like my cheat sheet. So when I want to look up how should I construct that, in what zone these objects will end in the end. Okay, so how is it useful? Let's look back at heap spraying. Remember, we want to do these 4 things. We want to allocate repeatedly, we want to allocate attacker-controlled data, large quantities, and fill it with a specific pattern. Unfortunately, there is no way to loop inside the plist. So if you want to allocate large quantities, you have to create, in this case, we use an array. We just create an array with many elements. So when you pass that to the kernel, it will create first a dictionary, then inside the dictionary an array, and inside the array will be a lot of strings. Yeah, and when you look at, I prepared this slide. When you look at this, this will look like this in memory. So you have the different kalloc zones and something which I call large because it will just be a very large block that will most probably not even be in your normal kalloc zones. Well, depends on how much memory you want to allocate. And then you can see in each zone what is created inside there and what is sent to each other if like the heap is cleaned in this case. So yeah, you can see that it always starts with the OS dictionary object, which is like 40 bytes in size, and this points to like yeah, the dictionary key and dictionary value. In our example, we just had like 1 element in there, so it's just like 8 bytes. So you see it's in the kalloc 8 zone, and the key pointer points to the actual key, and the dictionary value points to an array, which is again in the kalloc 40. This points to the array buckets, which is like in some large memory block. And inside the array inside the array buckets, there are pointers to all the OS string objects, which are 20 bytes in size, but they end up in the 24 bytes alloc zone, and each of these elements points to a string, which is like I think 9 bytes long, so it doesn't fit in the kalloc 8, so it was put into kalloc 16 zone. Yeah, so you can see by like just repeatedly ordering the kernel to create objects, they will be created. And by doing a very long plist, you can create a lot of elements. Okay, so so far we can allocate repeatedly, and we can allocate large quantities of data. So now we want to solve the other things. Yeah, the next thing we want to do is to allocate attacker-controlled data. We already saw, yeah, we can use strings, but the problem with strings is they are not completely attacker-controlled because strings cannot contain null bytes. So in order to have null bytes in your attacker-controlled spray, you need to use a data tag, which allows you to create like data blobs in memory, objects with data blobs. And the nice thing here is there are 2 different ways to specify that. You can either encode them base 64, or the kernel also supports a hex format. So you can just like do it like this. And again, I have, oh yeah, and the nice thing here is when you do the string thing, the parser actually creates a string that might interfere with the memory that's allocated in the kalloc zone. So that you don't have this problem when you lose data, because data blobs are parsed always in chunks of 4096 bytes. So these are most probably not the exact size that you want to attack. It's not in, it's in like in the big zone. So when it like parses this, it will not confuse the rest of the memory. Okay, and this allocation looks like this. Again, you have the dictionary, which points to the buckets, and the buckets contain the key and the array. And the array in this case contains OS data objects, and they point to arbitrary memory blobs. So this basically means all 4 properties that we need, all 4 things that we need to do for a heap spray are easily possible with a plist. You just have to make a long plist and put in the data you want to spray the heap with. So heap feng shui is a little bit more complicated. So again, we want to allocate repeatedly, but we already know that's easy. We already know that's easy, and we don't need to like find a new solution because we have the solution. And we also can allocate arbitrary sized memory blocks because we can allocate strings and data and we can make them short and long. But it's only orange here because if I overwrite a string, it's most probably not interesting for me. I want to have arbitrary sized blocks that contain useful information when I overwrite it. Okay, so how can I fill arbitrary sized memory blocks with actually data when I overwrite it? It's useful to me. And like I said before, for strings and data, this is actually not really useful because they are just strings and data. And if you overwrite them, that's maybe useful for information leakage, but it's not useful for actually code execution. So what I want to do is I want to allocate arbitrary sized blocks that are filled with, in this case, pointers to OS objects. And this is very easy because I can just create arrays with an arbitrary number of elements, and each element inside the array is like a pointer to an object, and if I manipulate this pointer, I can achieve code execution. So if I want to allocate like 344 bytes, I will just put this size and divide it by 4, and then I know how many elements I need to put into the array. And of course, I can do the same attack with dictionaries. In this case, I have to divide it by 8. Yeah, and you can see here, in this case, I always fill them with Boolean values because it makes the plist very short, and I can create a lot of elements with a very short plist. But in this case, I'm only interested to have like these array buckets that are in the size that I need them to be. Again, if you look at the how this looks in memory, it looks quite complicated, but what you need to know is just like you have like all the memory blocks in the different zones, and interesting here is that when the kernel creates booleans with OS unserialized XML, it doesn't really create the objects. It creates references to global true and false values. So in this case, all the Booleans that are inserted into these array buckets are actually not using more memory. They are just like using the pointers that is needed, because the pointer points to the global object, and this just increases and decreases the reference counter. And yeah, so in this case, there is no additional memory allocated for the elements inside the array, because they are all like global pointers. So, and this means we now are able to allocate arbitrary sized memory blocks, and additionally have them filled with stuff. If you override that or manipulate that, then we basically are already near code execution. So the next thing and the last thing we need is we need to be able to poke holes into this. And now you think, well, okay, you just give it objects and it creates these objects, but why should it like allow you to poke holes? And it actually doesn't allow you to do that, just like how it's implemented that it's possible. Because when you have a dictionary, you can insert stuff into the dictionary and give it like keys, arbitrary keys. And you can see in this example, I insert A, B, 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 C, 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 D, 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 E, 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 and in the end, I insert C, 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 C again. And what happens now is that when it tries to add it to the dictionary, it will see, oh, there's already an element with the same key, and it will just destroy the old allocated memory and yeah, replace that value, in this case again with a global pointer to this global Boolean true. So that looks like this. You have like this dictionary with a very large bucket for each dictionary key and value. And they point to the keys and they point to the data. And the data, of course, points to the data. And you can see in the middle there's this set. And we want to get rid of this set. So we just allocate some new value for CCCC. And then you have now instead a pointer to this global true value, and the OS data object and the data it points to are freed. So this is how you can poke arbitrary sized holes into the allocation. And when you combine all that, of course, you have everything that you need to do an actual heap spray or heap feng shui. Yeah, and that's basically more or less the end. Just a last slide for, there's a special gimmick. If you just want to crash the kernel, then you can just use the same function by, you just create some objects, and then you create references to it, and a lot of them. And this means this memory will never be freed after the IOKit API returns. And then you call it several times until the kernel runs out of memory, and then there you have like a kernel crash. Yeah, any questions? A little bit of like advertisement for our book. Yeah, if you want to get into iOS kernel exploitation or iOS exploitation, you should really look into this book. But are there any questions? Everybody wants to go to lunch.